Hello, my name is Jennifer Lee.
My name is Thomas Lambros.
And my name is Raven Santos.
And today we will be going over the heat pipe heat exchanger waste heat recovery AC system. So in terms of our presentation today, we will be going over our problem statement and design objectives, as well as our design diagram for our heat pipe heat exchanger, results from our code and SOLIDWORKS CFD model, cost analysis, and some references at the end. So our objective is to eliminate the energy losses of the reheating system in a traditional HVAC unit by incorporating a heat pipe heat exchanger system between the exhaust air of the AC and the incoming fresh air of the operating system. And so this is in between the returning air and the supplied air. This is to reduce the energy losses of the reheating system and the overall air treatment energy consumption. This heat pipe system consists of 8x6 rows of annular wick heat pipes to initialize the heat transfer between the different air volumes. And the objective of the system is to increase the efficiency of the traditional HVAC unit. And data shows that with this model of the secondary heat recovery, there's an increase of 40% in the summer months and 20% in the winter months.
Speaking of the fresh air, return air, and all those other things that Jen just brought up, this is a diagram of our design. Figure 1 shows a common heat recovery heat pipe heat exchanger AC system, which is basically it's actually even more sophisticated than what you would find in a normal house. In this one, the fresh air goes into a cooling coil, then the heat pipe, and then comes out as supply air, and it's collected again as return air, put back into the heat pipe, and then back into the cooling coil as to increase the efficiency. However, in figure 2, we have a secondary heat recovery heat pipe heat exchanger AC system, which does the same thing and a little bit more. The fresh air goes into the heat pipe, through there to the cooling coil, through there to the heat pipe, the second heat pipe, comes out as supply air and goes back in as return air, just like the last one, hits the heat pipe. And after the heat pipe, it actually is a liquid vapor mixture, saturated liquid vapor mixture. So some goes back into the cooling coil, some goes back into the cooling coil, while some goes back into the first heat pipe to increase the efficiency even more. Next slide. Now, when we were coding this, of course, we ran into problems, but for the most part, the article that you gave us, Professor, had most of the data we needed. A couple of things had to be assumed, including the wick thickness, which we used 12.954 times 10 to the negative 5 meters. Anything else? Yeah, the nomenclature of the article was rather odd, so we had to improvise a couple of things. They used B for pressure and interesting things. Celsius and Kelvin had a problem. We had to assume Reynolds number to be 2200 at first until we figured out later what would be most accurate, as well as a Mach number of 0.15. And we used the circular cylinder artery heat pipe equations that you can find on tables 4.1, 4.2, 4.3. And that gave us these capillary limits after we finally got to an answer. All of them pretty much make sense, at least in my eyes. Hopefully they do in yours too. The only one that's a little odd is the capillary limit, which is off by what seems to be about a factor of, about 1,000. So maybe we accidentally added a kilojoules to the bottom or something. I don't know. But there it is.
All right, and here is our SOLIDWORKS CAD model. So in order to simplify our system, in order to conduct a CFD analysis, I've utilized a single heat pipe out of the 48 that is in our system. And currently we have a total length of 680 millimeters. And the evaporator, adiabatic, and condenser sections are all of equivalent lengths, which is 226.66 millimeters. And for each component in this heat pipe, we use the material aluminum 6061, which is the same as as stated in the report. And on the bottom right, you can see the section separators, which is a small interface in order to create the different sections of the heat pipe. Here, we have a animation of the flow in the heat pipe, and as you can see in the first section separator, we have bottlenecking caused by As for our CFD constraints, we have an inlet mass flow rate of 2.5 kilograms per second, an environmental pressure of 1 atmosphere, and our heat transfer boundary condition is a constant surface heat flux of 64.17 kilowatts, which is divided by the total number of heat pipes. Our the surrounding temperature used is 40 degrees Celsius, and our working temperature range of liquid ammonia is between 5 degrees Celsius and 15 degrees Celsius. And here is our pressure contour from our CFD analysis. We can see that we have a high pressure starting at the evaporator section, and going down the heat pipe, we have a pressure drop, which is as expected. Here is our internal velocity contour, and the biggest issue encountered here is with these separator sections, and that causes a bottlenecking and essentially makes the flow restart as an undeveloped flow. Now here is our CFD fluid temperature contour, and this was our biggest issue in creating the CFD analysis, and this is due to not being able to model the heat pipe as a heat pipe. What we really have here is a hollow aluminum tube that has fluid flow going inside it because there's no wick. And this is what causes the incorrect temperature contour, and we hope to be able to fix this in the future.
All right, so going over some of the cost analysis. We are a service company located in Pomona, California. And so what this means is that we will source materials from direct suppliers and then install the heat pipe heat exchanger system into consumer households, inputting our design into current common HVAC systems for a price of about $1,500. And so analyzing the costs, I looked into fixed costs, which includes rent for a warehouse that will store our inventory, as well as utilities and insurance for that, and variable costs, which include material, the heat pipe heat exchanger materials, and the labor for our technicians that will go install. And once again, the price will be about $1,500. And calculating the break-even point, that was about 90 units per year or about 8 units per month. And so anything above that will be profit and anything below that will be a loss. So our goal annual rate of production is to be about 180 units per year or about 15 units per month. And this comes out to an annual profit of about $41,000. And this is after subtracting the expenses and accounting for income and property taxes as well. And here are some references that we use for our presentation.